Hello everyone, welcome back to Precalculus. Today we'll be covering section 1.4, composition of functions. First, we're going to review how to combine functions with algebraic operations like adding, subtracting, multiplying, dividing. Then we'll look at how to make and evaluate composite functions, and then we'll look at how to find the domain of a composite function. Additionally, you'll also learn how to decompose a function. So you already know you can take two functions and add them, multiply them, subtract them, do whatever to get a new function. For example, if we have f of x equals 2x plus 1 and g of x equals x squared, what is f plus g of x? We just take f of x, 2x plus 1, and add g of x, x squared. And you could reorder your terms, but that's pretty much your final answer. To find f times g of x, you take f of x, 2x plus 1, and you multiply that by g of x, x squared. That's it. Now, this little open circle right here means f of g of x. So this is the same as f of g of x. What does that really mean? Well, think about what you do when you plug in a value. Let's say f of 1. Whatever's inside these parentheses, you put in place of x. So in this case, since g of x is inside those parentheses, instead of putting x there, you should put g of x there. So you would have 2 times whatever g of x is, x squared plus 1, or 2x squared plus 1. That is f of g of x. Let's take a moment to note one slight off case. If we have f divided by g of x, your process is a little different. Of course, you still have whatever f of x was, 2x plus 1, over whatever g of x was, x squared. But in this case, now you have a domain restriction. Just make sure to be careful about your domain when you're dividing. Let's look at this example, where f of x equals x minus 3 and g of x equals x squared plus 2. We're asked to find f plus g of x and g of f of x. Let's start with f plus g of x. So we know f of x is x minus 3, and we're adding that to g of x, which is x squared plus 2. We can just simply add our like terms. We get x squared plus x minus 1. That's the answer. Now for g of f of x, you can write it out like this if it makes it a little easier to understand. So instead of an x here, you have f of x here. That means in place of all of your x's in your equation, so in place of this, you're going to put all of f of x. So you're going to have x minus 3 squared plus 2. Because think about it, this is normally where x would be, but instead, f of x is there. So you have x minus 3 squared, which is x squared minus 6x plus 9 plus 2. You get x squared minus 6x plus 11. And that is g of f of x. Let's take a look at another example of a composite function. Here we have f of x equals 3x minus 2, and g of x equals x squared plus 1. How do we find f of g of x? We know that this, with this little open circle, is the same as f of g of x. These are the same thing, right? So let's think about it this way. Here we have our input, and here we can see that our input lies here in our graph of f. F is what we would call our outside function. G of x is the inside function. So instead of putting x here, you're going to put all of g of x there. So in f of x, you would have 3 times x minus 2, right? But instead of x, you're going to have g of x. So you'll have 3 times x squared plus 1 minus 2, which is 3x squared plus 3 minus 2, or 3x squared plus 1. That is f of g of x. Now, with this new bit of knowledge that f of g of x is 3x squared plus 1, let's try to find f of g of 3 per se. So now that we know f of g of x is 3x squared plus 1, we can just plug in 3 for x, right? We'd have 3 times 3 squared plus 1, which is 27 plus 1, or 28, right? But there's also another way to do this. So we know for sure our final answer is going to be 28, so I'll leave that over here. But let's try the other method for doing this. We know that this is the same thing as f of g of 3, right? Because this is f of g of x right here, and this says that our x will be 3. So we just have to plug in 3 for x, and this part remains the same. So let's find the inside first, g of 3. So we plug in 3 for x and g of x, we get 3 squared plus 1, which is 10. So now we're looking for f of 10, right? Because we know g of 3 equals 10. We have f of x up here. Let's plug in 10 for x. We have 3 times 10 minus 2, which equals 30 minus 2, or 28. The same final answer we got up here. Sometimes it's much easier just to plug in x here instead of making the composite function, but I'd recommend you know how to do both. Here's what you need to know about finding the domain of f of g of x. Remember, f of g of x can be rewritten like this. I know I sound like a broken record, but please do not forget this. Here are the two things you need to find the domain. First, you need x such that x is in the domain of g. So x has to be in the domain of g. And then you need g of x must be in the domain of f. In other words, the x's that you can give to g also must produce g's that can go into f. Here we have an example of finding the domain of a composite function. Remember your two rules. X must be in the domain of the inner function, and the inner function must be in the domain of the outer function. In this case, our inner function is g, and our outer function is f. So we need x that fits in the domain of g. Well, if you look at g, you can plug in anything for x. So our domain of g, I'll put like sub g, is from negative infinity to infinity. It's all real numbers. Now our domain of f looks like, for the square root of x, it has to be greater than or equal to 0. So our domain of f is 0 to infinity with 0 included. Now, to find the domain of f of g, you have to find places where g of x is in the domain of f. Well, what does that mean? You need to find places where this falls into this category. You need places where x minus 2 is greater than or equal to 0. So x has to be greater than or equal to 2 if you add 2 to both sides. Therefore, the domain of f of g of x is from 2 to infinity with 2 included. Let's take a look at this example. In this case, we have f of x equals 1 over x. So I can already see that the domain of f of x, so domain of f, is all real numbers, so from negative infinity to 0, union 0 to infinity, because it can be all real numbers except for 0. If x is 0, you get 1 over 0, which you can't have. Now let's look for the domain of g. The domain of g. For g of x, we have a radical, and inside the radical is x plus 1. We know the inside of radicals has to be greater than or equal to 0, so if we set x plus 1 greater than or equal to 0, subtract 1 from both sides, x is greater than or equal to negative 1. So we know for the domain of g, we have negative 1 included to infinity. Now let's actually construct our composite function to see how much of each of these we need to use. So if g is the inner function, we're plugging that in for x of our outer function. So instead of 1 over x, we're going to have 1 over the square root of x plus 1. Now in this case, you can see that the entire denominator cannot be 0. So root x plus 1 cannot equal 0. And we also know that x plus 1 has to be greater than or equal to 0. So this is the domain of the composite. Let's look at this a little deeper. So we know x has to be greater than or equal to negative 1 again because of this portion, but we also know that square root of x plus 1 cannot equal 0. Well, if we square both sides, we get x plus 1 cannot equal 0, and then we subtract 1 from both sides, x cannot be negative 1. So we see that the two pieces of our domain, x is greater than or equal to 1, or negative 1, and x cannot equal -1. So we know on a number line, we'd have an open circle at -1, and we'd want all the values greater than -1. I know it seems a little odd that here we said it has to equal, and here we said it cannot equal, but this will take precedence, because piece of this is still true. Piece of this is still true. If you plug in values greater than -1, you would still have a perfectly fine function. However, if you plugged in -1, there would be an error in your whole function. You have to put both pieces together and incorporate them both. You cannot say that one will eliminate the other. In this example, this one does cut out part of another, but it does not completely overwrite it. Both of them are incorporated. So, let's talk about decomposition. When we were composing functions, we were given an inner and outer function, and then we combined them together. This one, we're given an already combined function, and we must determine what our inner and outer functions are. In this case, we have h of x equals the quantity 2x plus 1 cubed. In this example, it's quite easy to see what is your inner and outer function. You can see your outer function probably has to do with this cube, and your inner function is probably what's in here. So let's write them as an inner and outer function. Let's say our inner function, or in this case, g, because that's what we're asked to find, asked to find f of g. So g is our inner function. Let's say g is 2x plus 1. g of x equals 2x plus 1. Now, for f of x, you need to find a way to replace your inner function with x. And I'll explain what that means in a minute when I show you how to do this backwards. So if I were to replace this entire inner function with x, I would have x cubed. So f of x equals x cubed. Now I know we made kind of a leap in judgment there, but let me show you why that works. If this is our inner function and this is our outer function, let's try to combine them back together. To find f of g of x, I would plug in g of x in place of x here, right? So f of g of x would equal 2x plus 1, because that's what our x is. This is where our x is, cubed, which is what we started with, 2x plus 1 cubed. You have to find a way to determine what your inner and outer function are. Just remember, your inner function is what you're plugging in to a different function, so your inner function should be replaced with just x. In this example, we have h of x equals e to the 3x. In this one, it's a little harder to find what your inner and outer function is. But remember, you're plugging in one function, you're plugging in g into f. So can you find an f in which you can plug in something else to combine to get e to the 3x? Let's try getting rid of this 3x. Let's say our outer function, f of x, equals e to the x. Now, what could I make g of x so that in place of this x, you would have 3x? You could say g of x simply equals 3x. That's it. Because if you compose this backwards, f of g of x, you would get e, and in place of your x, you have g of x, 3x. If you can easily identify your inner and outer function, this whole process becomes a lot easier. This process might seem a little useless at first, but let's take a look at what this could mean in real life. Let's say you have a function g of t, where you plug in a time and you get a temperature. Now let's say you have a function c of g, where you plug in a temperature and you get cost, maybe your bills, like your energy bill, for having to lower or increase the temperature in your house. If you composed those two functions together, instead of plugging in time getting temperature, plugging in temperature getting cost, you're plugging in time and you're getting cost right out. So now you've remapped the whole thing. Instead of going from t to g and g to c, you're going straight from t to c. In summary, you can combine functions algebraically using plus, minus, multiplication, or division. You can do f plus g, f minus g, f times g, or f divided by g, or any functions together. Composition, f of g, means f of g of x, and the order matters. If I did g dot f then I would have g of f of x, which is a completely different thing. Decomposition is the reverse process of composition. Before you go, I have a few practice problems for you to try. Here are your practice problems. You can either pause now and try, or I'll give you the answers and work in 3, 2, 1. Here are your answers. Thanks for watching. My tutoring email will be in the description, and I'll see you next time for Precalculus 1.5.